Here's an example of some AP style questions in reference to this potential energy diagram. So we've got potential energy, which technically is starting off above zero, positive, and moving down below zero, negative. And we think of this as the energy released when a bond forms, or I could think of it as the amount of energy I would have to add in order to break a bond. So the lower that point at the bottom of the graph, the more energy released when the bond formed, or the more energy needed to break the bond. Then I've got internuclear distance, which is the distance between the two nuclei of bonded atoms. And there's kind of two things that will affect that. One is the size of the atom. Am I dealing with big atoms or small atoms? And number two, how closely are these atoms bonded to each other? Is it single bonds, double bonds, or triple bonds? So here we've got the potential energy diagram for a fluorine-fluorine bond. So this is for a fluorine-fluorine bond. Let's make that skinnier. There. Here we go. This is for the fluorine-fluorine bond. Often on the AP test, they'll have you comparing different diagrams, or they might ask you something like this. Carefully sketch a potential energy curve showing the relative potential energy and internuclear distance for something different. So the first one is a bromine-bromine bond. And in my head I'm thinking, okay, these are two different atoms, but they're both going to be single bonded. Like they both have 7 valence electrons. They'll single bond to get their octet. But I also know that fluorine atoms are going to be pretty small, and bromine atoms will be much larger. Bromine with the electrons distributed amongst more energy levels. Here's my periodic trends coming back into play. Okay, so then I have to think, well, how does that affect the internuclear distance? Well, obviously it's going to be on average larger. The distance between smaller atoms is shorter. And the internuclear distance when I have larger bonded atoms will be larger. Okay, so I want the low point on the graph to be at a greater internuclear distance. Well, then I think about potential energy. So potential energy, the amount of energy needed to break the bond, or the amount of energy released when the bond forms. Well, if I've got smaller atoms, they're going to pack tighter, and it's going to take more energy to break apart this fluorine-fluorine bond, which also means that more energy must be released when the bond forms. So I want to draw a graph that might look something like this. Maybe something like that this blue one is my bromine-bromine bond, where the only point that I really care about on these graphs is that low point. And I say, okay, these atoms are larger, so they should be at a larger internuclear distance. So that low point should be farther to the right. But I also know that it would take less energy to break this bond. The atoms are bigger, and so they're going to be a little further from each other. And so I want it to be at a little higher potential energy level. Less energy would be released when the bond formed. Less energy needed to break the bond. The second example has us carefully sketching a potential energy curve showing the relative potential energy and internuclear distance for a nitrogen-nitrogen triple bond. Okay, so I didn't have to draw the dot structure. They're telling me that it's a triple bond. And I think about like a triple bond, and I know that it's a stronger bond. It's going to take more energy to break a triple bond, so more energy would be released when the triple bond forms. So the low point should be lower than this one. If this is the fluorine-fluorine bond, that lowest point is going to be lower for the triple bond. More energy released when a triple bond forms, more energy needed to break a triple bond. Now, nitrogen and fluorine are relatively close to each other on the periodic table, so their radii are similar. I mean, maybe technically fluorine's a touch smaller. But then I have to weigh that against the fact that this nitrogen bond is a triple bond. And you can see it like if you were to build a ball and stick model, that triple bonds are really short bonds, where in order to get the orbitals to overlap, you have to pull them pretty close to each other. So again, even though these atoms are pretty similar in radius, and maybe just like the straight up radius of a fluorine atom is a touch smaller, because of that triple bond, we're going to have a smaller internuclear distance. Internuclear distance. Now the distance is really about the fact that this is a triple versus a single. And these are, again, atoms that are in the same energy level, so their initial radius is pretty similar. Whereas in the first one, I've got two atoms that have very different radii, but the same kind of bond. They're both singles. So it wouldn't be fair of us to sketch a graph where they're changing too many variables all at once. And maybe they could show me the graph, but here I'm really looking at, in the first graph, the distance versus potential energy when I've got different sized atoms. And in the second, I'm looking at the effect of that triple bond versus a single. So I want a smaller internuclear distance, and I want a larger potential energy. So maybe something that looks kind of like this, where maybe down here, this is my nitrogen triple. More energy released when the bond forms, meaning more energy needed to break the triple bond. And it should be at a little shorter internuclear distance, which would mean like closer to the left, I would find that lowest point. A triple bond is a shorter, stronger bond.